So let's proceed now to a discussion of a very important state function known as the Gibbs free energy. And this is a state function that actually determines whether or not a reaction will be spontaneous. So if you recall, we talked about the fact that we determined that for most spontaneous reactions, delta H is negative. In other words, a reaction is exothermic, but that is not always true. There are some instances where the enthalpy change is positive and the reaction is still spontaneous, all right? So it turns out that this particular state function, Gibbs free energy, is basically very useful for predicting spontaneity. But let's define what we mean by it first. Um, so here's a definition here: the energy associated with a chemical reaction that can be used to do work. And there's an equation for the Gibbs free energy, which is shown right here for reaction, whenever the temperature is constant. So this is the definition, mathematically speaking. Delta G is equal to the enthalpy change of the system minus T times the entropy change of the system, right? And here is where Gibbs free energy helps us to determine whether or not a reaction is spontaneous. Basically, if delta G is negative, then the reaction is spontaneous in the forward direction. And if delta G is positive, then the reaction is non-spontaneous as it is written, but spontaneous in the reverse direction. So this is what we can use to basically predict whether or not a reaction will be spontaneous. Another thing we need to recognize that when delta G is equal to 0, then the reaction is at equilibrium, which means that the rate of the forward reaction is equal to the rate of the reverse reaction. All right, so delta G, the Gibbs free energy, is very useful for making those kinds of predictions. Now, the standard free energy is a free energy for a reaction when it undergoes, when it occurs under standard conditions. And we talked about the standard conditions already: pressure being 1 atmosphere, temperature being 25 degrees Celsius. And we can actually calculate the Gibbs free energy for a reaction because if you're given the standard free energy of the individual substances, then basically it's the same products minus reactants arrangement, just as we had with entropy and in enthalpy. Same thing applies for delta G. And there are tables, of course, for giving you the enthalpy, or I should say the free energy of formation, which is what the definition here is telling you it is. It is the free energy change when 1 mole of a compound is formed from its elements in its standard state. So it's kind of similar to enthalpy of formation standard that you would have learned about in General Chemistry 1. So just as though we have a table of values for the enthalpy of formation of under standard conditions for different substances, we have similar tables for standard free energy of formation, all right, for different substances. And another thing you need to see or need to recognize, which is, again, something in common with enthalpy of formation for different substances. For elements, that value would be 0, all right? Okay, so with that said, we can simply apply what we just learned to this problem here. Question is asking for the standard free energy change of the following reaction at 25 degrees Celsius. Well, that's very simple. It's basically products minus reactants, and we set up our equation. Of course, we have to multiply the free energy of formation standard for the different substances by their respective coefficients. So you notice there's a 12 here for carbon dioxide, a 6 here for water, because those are the coefficients of those substances in the balance equation. There's a 2 here for benzene, C6H6, and oxygen is an element, so therefore its enthalpy of, not enthalpy, I'm sorry, free energy of formation will be 0. So of course we don't include that here. And then all you have to do is plug the numbers in. Of course, these numbers you'd get from the tables. And according to the calculation here, this works out to be equal to minus 6,405. All right, so that's basically how that is done. All right. So the next question is this reaction spontaneous at 25 degrees Celsius? Well, the answer is yes, because since delta G here, standard, is negative, that means that the reaction is spontaneous. So that's a relatively simple example of how to calculate the standard free energy change for a given equation. Okay, going back to this equation, I think it's important that we recognize how the sign of delta G can be affected by the sign of delta H. and the sign of delta S. All right. So I stated here, and this table basically summarizes the different possibilities. So let's look at the first possibility here. If delta H is positive, if delta H is positive and delta S is positive, then whether or not the reaction is spontaneous depends on whether or not the temperature is high or low. So if this temperature is high, these two terms are positive, right? That means delta G would be negative, and therefore the reaction would be spontaneous if the temperatures are high, such that delta H is less than T delta S. Now, if the temperature is low, then the reverse will be true, which would mean that delta G will be positive, and therefore the reaction will be non-spontaneous in that direction. Now, if delta H is positive and delta S is negative, right, that means that delta G is always going to be positive, right? Because basically this will be positive, and because this is negative, that negative sign makes all of this positive, so that means delta G would be positive, which means that the reaction would be non-spontaneous. So it doesn't matter what the temperature is, basically the reaction will be spontaneous in the reverse direction. Okay, if we switch these two, so delta H is negative and delta S is positive. So if this is negative, whoops, I'm sorry. If this is negative and this is positive, that means delta G is always going to be negative, which means that the reaction is going to be spontaneous. And then finally, if delta H is negative and delta S is negative, then again, it depends on whether or not the temperature is high or low. So if the temperature is high, that means that delta G is going to be negative. The temperature is low. That means that delta G is going to be negative, and therefore the reaction will be spontaneous. But if the temperature is high, that means that the reaction will be spontaneous, all right? Or the reverse reaction will be spontaneous. So as you can see, the sign of delta G is dependent on whether or not delta H and delta S are negative, positive, whatever. There are different possibilities as summarized in this table. Okay, another thing we want to talk about is the relationship between Gibbs free energy and chemical equilibrium. And it turns out that the free energy of reaction is related to the reaction quotient by this equation. Delta G is equal to delta G standard plus RT ln Q. R, of course, is a molar gas constant, which in this case would be 8.31 joules per mole Kelvin, and temperature, of course, would be in Kelvin. And Q is the reaction quotient, which, if you recall from the previous chapter, or previous chapters, it's the concentration of the products over reactants at any time, not necessarily at equilibrium. So as I said before, R is a molar gas constant, and the T is the temperature in Kelvin, and Q is a reaction quotient. Now, at equilibrium, delta G is going to be equal to 0, right? Which means that this term here on the right side, all of this here would be equal to 0. And also at equilibrium, Q is going to be equal to K. So if we substitute K for Q in this equation and 0 here, this is the expression we're going to get. 0 is equal to delta G standard plus RT ln K. And this can be rearranged to get delta G standard is equal to minus RT ln K. And if you look at this equation carefully, you'll see that there's a sort of inverse relationship between the equilibrium constant and the delta G standard, right? In that, the larger the value of K, the more negative this term is, and therefore the lower would be the delta G standard, all right? So delta G standard represents, of course, under standard conditions, a reaction that is spontaneous. So a reaction that is spontaneous would mean that the K value would be relatively large, definitely greater than 1, all right? And this table here kind of, or these graphs, I should say, I think represents very well the relationship between Q and K and delta G, all right? So this graph over here represents a situation where delta G is negative. So we're talking about a spontaneous reaction going from pure reactants to pure products. So as you go from reactants to products, the free energy falls until you get to a minimum here, and that's the equilibrium position where the free energy is at a minimum, right? That's where Q is equal to K. Before that, Q was less than K, so the reaction has to proceed to equilibrium here. Or if you start from here, pure products, as the reaction goes to equilibrium, because Q is greater than K, what you'll find is that delta G or G would decrease until you get to this point right here. Now, the actual delta G value is, of course, the difference between the G of the reactant standard minus, well, actually, it's the other way around, the G of the products minus the G of the reactant. So, therefore, in this case, delta G is negative, which means that the reaction is spontaneous. In this case, however, things are reversed, right? Delta G is positive, which means that as the reaction goes from reactants to products, the energy falls here. I'm sorry. And then the same thing happens going from the products to reactants. The energy falls until you get to that equilibrium state. Again, delta G here is given. In this case, however, delta G is positive because the free energy of the products is greater than the free energy of the reactants. All right, so this basically summarizes the relationship, as I said before, between delta G, Q, and K, and also it shows you where the equilibrium positions are and how you calculate delta G based on the graph. Okay, so this is what I was alluding to earlier when I was saying that there's a sort of inverse relationship between delta G standard and K, right? So if K is greater than 1, that means that ln K is positive, which means that delta G standard is negative. And of course, what that means is that at equilibrium, you're going to have more products over reactants. When K is equal to 1, ln K is equal to 0, delta G standard is 0, which means that the products and reactants are equally favored at equilibrium. And then finally, if K is equal to 1, because of this negative sign, delta G standard is negative, which means that is positive, I should say, which means that the reactants are favored over the products at equilibrium. All right, so that gives you a feel for the relationship between delta G and K. Okay, and finally, I want to show you a biological application of what we have been learning about, all right? Now, as you know, in the human body, there's always a synthesis of protein, right? If you have done any biology, you know that to be the case, right? But it turns out that the actual synthesis of protein is one that is not thermodynamically favored because delta G for the synthesis of proteins is positive. So for example, just to see an example here of a simple dipeptide formed between alanine and glycine, it forms alanyl glycine. Delta G standard for this is plus 29 kilojoules. So therefore, what this is saying is that this reaction is non-spontaneous. What that means, therefore, is that in order for this reaction to take place, energy has to come from somewhere so as to drive that reaction to favor the formation of the dipeptide. So the question now becomes where that energy comes from. And the answer comes from glucose. Glucose, when it undergoes changes, of course, breakdown in the body, that's an exothermic process which provides energy. That energy converts ADP to ATP, which kind of serves as a storage for energy. And that energy from the ATP is basically transferred to this system here so as to facilitate the formation of proteins from amino acids. So basically what we have happening here is basically a coupling of this reaction to the reaction involving the synthesis of protein. And when that coupling takes place, this is what happens. The ATP plus water plus the 2 amino acid gives you the ADP plus phosphoric acid and the dipeptide. And when the free energy is measured for this reaction, you see that the free energy is negative, and therefore that tells you that this reaction will be spontaneous when the synthesis of proteins is coupled to the reaction where ATP forms ADP, right? So this is just a biological example of the application of thermodynamics, the principles that we have learned in this chapter. Okay, so that's it for this chapter. The next chapter is going to be dealing with